quick recap of these last few sessions. We're looking at the LDA method. LDA is linear discriminant analysis. It's a second type of classification model. The first one being logistic regression. What is a classification model? It's when the response variable doesn't take on numerical outputs, but instead we're looking at what we refer to as classes, hence the name classification models. Logistic regression, in the way the book treats classification models, logistic regression is used when the response variable y takes on two classes. It is a binary response variable with, for instance, yes, no, defaults, does not default on their loan, looking at each observation. For a lending institution, looking at their historical data. And you attempt to predict the odds of a default and by extension subtracting from one of not defaulting based on one or more predictor variables. These may be quantitative, such as the credit card balance, or else qualitative, such as the student status. Now we're using linear discriminant analysis as opposed to logistic regression when the response variable may take on more than two classes. And did we have any examples over here? I'm sure we did somewhere, but very often we were mentioning, and we took this from one section of the book, an emergency room, and you're classifying patients under seizure, drug overdose, and stroke. Again, based on one or more characteristics. For each observation, you have a set of characteristics, and those are the x's. If it's only one characteristic, that's p equals 1, where we use these normal probability density functions. If it's more than a single characteristic, that's p is greater than 1, the predictor variables are enumerated from x1 to xp. When p is 2, which is probably the best that our minds can do in terms of visualizing the information, we get these fascinating diagrams of multivariate normal density functions, where in the case of two predictors, x1 and x2, the probability is no longer the area under a curve, but it is the volume under these bell-shaped surfaces. This is a sort of a specific example. It's still three-dimensional. Remember, the color, the greens, oranges, and blues are giving us the third dimension. It is, in fact, what you're trying to predict. And we draw these decision boundaries. So, or really the model, we use Bayes' theorem and the LDA method which uses formulae like 4.19 to create these decision boundaries. Once the boundary has been drawn, what the model is telling you is that all observations with x1, x2 characteristics within, for example, this pink region, these will be classified as class blue, or whatever class blue is. It could be, for example, seizure, or you name it. Of course, it doesn't get them all right. It is misclassifying, for example, these two sort of color gold data points, but it's doing quite a good job, right? At grouping the blue data points in a single class, and the same for the green and the gold. Now, let's see exactly. We had arrived up to, I don't seem to remember reading any of that. So it's quite text heavy. Maybe we take a step back and we just start reading from maybe over here. Okay, let's do it. To indicate that a p-dimensional random variable x has a multivariate Gaussian distribution, we write x is distributed as a normal distribution with mean mu and covariance matrix sigma. Here, the expectation of x is equal to mu, and that's the mean of x, and it's a vector with p components. What does that mean? What does that mean? That means that you have your expectation for x1, so think of it as the mean of x1, the mean of x2, until the mean of xp. That's mu. It's a vector, although it's not in bold. We've often discussed this. The book doesn't really distinguish in terms of along notational lines. It doesn't really spend its time using bold or not bold. It's the context. It is assumed that the context is enough for us to understand what we're looking at. So mu is a vector with p components. The covariance of x is equal to sigma, is a p by p covariance matrix of x. Formally, the multivariate Gaussian density is defined as this over here. Okay, so it gives you a real number. It gives you one real number, and you sort of think of it as a probability. So x might be, you're sort of saying the probability, although strictly speaking, it's not a probability. The probability is when you speak of like an area under a curve. You take a rectangle, you sort of take like a rectangular strip, sort of like what's actually going on in the real data, and that area translates into the probability or the volume under the surface. But of course, you could have higher dimensional. You could have, if area and volume are, think of them as units squared or units cubed. You may very easily have higher dimensions. So this is a real number, and it depends on the characteristics over here. In the case of p is greater than 1 predictors, the LDA classifier assumes that the observations in the kth class are drawn from a multivariate Gaussian distribution with mean mu k and covariance matrix sigma. So they all have, do you remember when p was 1? We were assuming a Gaussian curve for each class. So we were saying, for example, the probability that, I don't know, a bird lives between 2 to 4 years, given that the bird is, I don't know, a female bird. The probability that the bird lives, unfortunately, these are negative numbers, but anyway, between negative, whatever that means, yours doesn't make much sense. But that the probability that the bird lives between these ages, given that it is a male. We're doing the same thing. We're doing the same thing for each class. For each class, we assume a Gaussian distribution, but it's a multivariate Gaussian. So you're going to have a bell. Just think of it. Probably the easiest thing is to always imagine the case where you have 2 dimensions. So at least you can visualize diagrams like these two. And for each class, so this diagram is 3 classes. An example with 3 classes. And each ellipse is the multivariate Gaussian distribution that we're assuming. Plugging the density function for the kth class, fk x equals k, into 4.10, and perform a bit of algebra, which we're not going to do, reveals that the base classifier, so 4.10 it's the key to everything, right? It is Bayes' theorem. And you get this. So for every vector, if you have a specific observation of interest, you look at its x characteristics, all p of them. You calculate this for those p characteristics. Most of the things that you're seeing over here are vectors. You get one real number. And for whichever class you get the largest real number, you get the largest delta, then you will classify that observation within this class. So you do, for example, in this case, we have 3 classes. So you calculate this 3 times. Really, the only difference in calculation is the mu k's will be different. That's the mean. And the pi k's will be different. This is the vector matrix version of 4.13. 4.13 being this one over here. An example is shown in the left-hand panel of figure 4.6, this left one over there. 3 equally sized Gaussian classes are shown with class-specific mean vectors and a common covariance matrix. So where is their mean? Their mean, I think, will be in the middle. So this is the mu green, the mu blue, and the mu gold. They have the same covariance matrix. And in fact, the ellipses are spread out in the same way. They have the same covariance, is what it's called. The 3 ellipses represent regions that contain 95% of the probability for each of the classes. This gives you 100%. So theoretically, over here, the probability won't be exactly 0. It will be very close. The surface would be, what's the word? Like an asymptote. So it would be very, very close to touching the plane. So there would be no volume. There'd be practically no volume. So what the book is doing is it's saying we're going to take an ellipse where it extends outwards enough to incorporate 95% of the probability under the surface if it's p equals 2. The dashed lines are the Bayes decision boundaries. In other words, they represent the set of values for which, what is this? Delta K is equal to delta L. Right. That's where exactly on the boundary, it could go either way. Classify it as a green, classify it as a blue. Note that there are 3 lines representing the Bayes decision boundaries because there are 3 pairs of classes among the 3 classes. That is, one Bayes decision boundary separates class 1 from class 2, one separates class 1 from class 3, and one separates class 2 from class 3. These 3 Bayes decision boundaries divide the predictor space into 3 regions. The Bayes classifier will classify an observation according to the region in which it is located. And I think we've understood this. Once again, we need to estimate the unknown parameters. So in real life, you wouldn't know the true mean of each multivariate distribution. Neither would you know the priors, which appear in Bayes' theorem. Neither would you know the covariance matrix. But just like when we had one predictor variable, there are these formulae that give you an estimate of the mu k's, the sigmas, and the pi k's. The pi k is just the prior probability. So just like we have those formulae, when p is greater than 1, the formulas are similar. I don't think the book quotes them. We'll just calculate them in R. The formulas are similar to those used in the one-dimensional case given in equation 4.15. To assign a new observation x equals x, LDA plugs these estimates into 4.19 and classifies to the class for which delta hat k of x is largest. Note that in 4.19, delta k is a linear function of x. That is, the LDA decision rule depends on x only through a linear combination of its elements. Once again, this is the reason for the word linear in LDA. In the right-hand panel of figure 4.6, we're now looking at, think of it as raw data. 20 observations drawn from each of the 3 classes are displayed, and the resulting LDA decision boundaries are shown as solid black lines. Overall, the LDA decision boundaries are pretty close to the Bayes decision boundaries, shown again as dashed lines. The test error rates for the Bayes and LDA classifiers are 0.07 and 0.07. What is a test error rate? A test error rate is checking how many you get wrong. So if we look at, but do ask questions when necessary. Let's see. I'm sure we must have mentioned, here we go, the error rate. Okay, remember when we calculated the error rate for this decision boundary, it was like getting 2 out of every 10 wrong, roughly. It misclassifies this pink one as a green, and it misclassifies these greens as pink. Same kind of thing over here, where you're misclassifying this green one, you're misclassifying these orange ones or these gold ones. Now, the LDA model fit to the 10,000 training samples results in a training error rate of 2.75%. Wait a minute. Let's just have a look. I think I have to start reading from here. We can perform LDA on the default data in order to predict whether or not an individual will default on the basis of credit card balance and student status. We may be doing this in the labs later on, possibly in this session itself. The LDA model fit to the 10,000 training samples, these are just your observations, results in a training error rate of 2.75. Okay, so what is this? So this means in the, going back to the default data, the LDA only misclassifies 2.75% of the training set's data, meaning what is 2.75 of 10,000? I think it's to 175, isn't it? So it only gets, of these 10,000, it only gets 275 wrong. What does wrong mean? Meaning it's an observation that did default, but the model classifies it as no default, and vice versa. An observation that did not default, but the model's decision boundary results in it being classified as a default. So this sounds like a low error rate, but two caveats must be noted. It's always the same one. First of all, training error rates will usually be lower than test error rates. In fact, we've often mentioned the competitions hosted on Kaggle. You win by obtaining the lowest mean square error rate, or in this case, I guess it would be the training error rate from all contestants, from all models. But that's calculated on the basis of data that was not available to the contestants. That would be the actual test error rate. So reading it again, first of all, training error rates will usually be lower than test error rates, which are the real quantity of interest. In other words, we might expect this classifier to perform worse if we use it to predict whether or not a new set of individuals, a set of individuals that was not used to design or to parameterize the model, will default. The reason is that we specifically adjust the parameters of our model to do well on the training data. The higher the ratio of parameters P to number of samples N, the more we expect this overfitting to play a role. For these data, we don't expect this to be a problem. Since P is equal to 4, why is P equal to 4? Because we've used credit card balance, student status. So why P equals 4? Isn't that only 2? Credit card balance, that's number 1. Student status, that's number 2. Not entirely sure. Would I go so far and say that this might be a typo? In fact, even if we go into our studio, I don't even think that there is enough data. Do I have it typed somewhere? Let's type over here. So that, and if we do data was it default? This, and we do structure default. Can we even take P of 4? No, right? You would take these 3 as your predictor variables that if you choose to use the full extent of the data set. And then this 4th one is not one of the predictor variables. So I'm not entirely sure, but the point is, the lower the ratio is of predictor variables to observations, then the less likely it is that there is overfitting, which is good. You want to avoid a model where there is too much overfitting, and this overfitting can be quantified. Going back to chapter 2, you look at. I'm actually like to look it up. I think it had to do with the bias or the rigidity. There is a way of quantifying. Anyway, never mind. We're back to where we were. Second, since only 3.33% of the individuals in the training sample defaulted, a simple but useless classifier that always predicts that each individual will not default. I got lost. Let's read it again. Second, since only this many individuals, or this percentage of the individuals in the training sample defaulted, a simple but useless classifier that always predicts that each individual will not default, regardless of his or her credit card balance and student status, will result in an error rate of 3.33%. In other words, the trivial null classifier, I think that's when you're not using any predictor variable, will achieve an error rate that is only a bit higher than the LDA training set error rate. So I think what we're saying is, although 2.75% looks low, when you actually compare it to the number of individuals that did default, it's actually quite a high error relative to the number of people that actually did default. And in fact, we have the numbers in this so-called confusion matrix. So you take your 10,000 people, your 10,000 observations, and you partition them into 4 categories. And well, yeah, into 4 categories based on the actual data and the predicted data. So which are the ones that we get right? The ones that this model got correct are these 2. Whereas the other 2 are known as false positives and false negatives. Self-explanatory, right? These 23 are false positives. The model predicted them as yes, default, but in fact they had not defaulted. These are false negatives, and these are the ones the bank really needs to watch out for. This is where the model is predicting that they're not expected to default. So trusting the model blindly would result in offering them a loan, but the bank, but in fact they actually defaulted. So how do we calculate that what was it? 2.75% error. You just add these 2. I think you just add these two, right? You add the false positives and the false negatives. 252 plus 23, that's 275. Yeah, 275 of these 10,000, the model got wrong. In practice, a binary classifier such as this one can make two types of errors. It can, this is what we just discussed, it can incorrectly assign an individual who defaults to the no default category, or it can incorrectly assign an individual who does not default to the default category. It is often of interest to determine which of these two types of errors are being made. A confusion matrix, which is what we just discussed, is a convenient way to display this information. The table reveals that the LDA predicted that a total of 104 people would default. Of these people, 81 actually defaulted and 23 did not. Hence, only 23 out of 9667 of the individuals who did not default were incorrectly labeled. This looks like a pretty low error rate. However, of the 333 individuals who defaulted, 252 were missed by the LDA. So while the overall error rate is low, the error rate among individuals who defaulted is very high. From the perspective of a credit card company that is trying to identify high-risk individuals, an error rate of 252 out of 333, 75%, among individuals who default may well be unacceptable. So this is exactly what's going on, right? From the 333 people that really did default, you've actually classified 252 of them as not defaulting, not a very it's not very promising. So instead of looking at the overall numbers from the perspective of a credit card company, you're really interested in the ones that did default. And the model using LDA actually got all these wrong. It incorrectly classified them as did not default. Class-specific performance is also important in medicine and biology, where the terms sensitivity and specificity characterize the performance of a classifier or screening test. In this case, the sensitivity is the percentage of the true defaulters that are identified, a low 24.3%, meaning the 81 out of the 333. The specificity is the percentage of non-defaulters that are correctly identified. So correctly identified. So it would be the 9644 out of 9667, which is 99.8%. Why does LDA do such a poor job of classifying the customers who default? In other words, why does it have such a low sensitivity? As you have seen, LDA is trying to approximate the base classifier, which has the lowest total error rate out of all classifiers, if the Gaussian model is correct. That is, the base classifier will yield the smallest possible total number of misclassified observations, irrespective of which class the errors come from. That is, some misclassifications will result from incorrectly assigning a customer who does not default to the default class, and others will result from incorrectly assigning a customer who defaults to the non-default class. In contrast to the way the model works, a credit card company, as you would expect, might particularly wish to avoid incorrectly classifying an individual who will default. These are the real dangerous ones, right? It doesn't matter maybe if someone was actually had a very good risk profile, and maybe you decline to lend them any money. But the real dangerous ones are these: incorrectly classifying an individual who will default. Whereas incorrectly classifying an individual who will not default, though still to be avoided, is less problematic. We will now see that it is possible to modify LDA in order to develop a classifier that better meets the credit card company's needs. Okay, I think this is where we're going to use a threshold. So the base classifier works by assigning an observation to the class. Do you remember this? For which the posterior probability pk of x is greatest. Isn't this how Bayes works? Well, not Bayes, the Bayes classifier. For every, you give it an observation. When we say you give it an observation, you give it the characteristics of that observation. For example, student status and credit card balance. It's a two-component predictor variable. And for that observation, it calculates the probability of the observation being in class K given its characteristics. So the probability that we have class K given X. It calculates for every class, and then the one that gets the highest, the class that gives you the greatest posterior probability is the class to which we will assign the observation. Now, in the two-class case, this amounts to assigning an observation to the default class if the pk is greater than 0.5, right? If it's only two classes, if it's only two classes, then what you would expect is which pk wins? Well, the one with more than 0.5 as an output. And please, I'm trying to match all the colors so that we can see exactly what we're referring to. So the Bayes classifier, and by extension LDA, uses a threshold of 50% for the posterior probability of default in order to assign an observation to the default class. However, if we are concerned about incorrectly predicting the default status for individuals who default, then we can consider lowering this threshold. For instance, we might label any customer with a posterior probability above only 20% to the default class. So that's a decision, that's kind of like a manual intervention. Just going to mute the mic. In other words, instead of assigning an observation to the default class, if 4.21 holds, we could instead assign an observation to this class if the probability that default is equal to yes, given that x is equal to x, is greater than 0.2. The error rates that result from taking this approach are shown in table 4.5. Okay. So now we have this table. Now this is doing a much better job now, isn't it? Of course, it's if we compare them, instead of misclassifying 23 no's as yes, it's classifying a lot more. It's classifying 2, 3, 5 true no's as yes. But that's the price we're willing to pay, because now instead of only getting 81 of the yes default correct and classifying as a yes, it gets 195, which is going to be now more than 50% of the yeses. Now, LDA predicts that 430 individuals will default. Of the 333 individuals who default, LDA correctly predicts all but 138, or 41.4%. This is a vast improvement over the error rate of 75.7% that resulted from using the threshold of 50%. However, this improvement comes at a cost. Now, 235 individuals who do not default, these 235 are incorrectly classified. As a result, the overall error rate has increased slightly to 3.73%, but a credit card, now let's see it from the practical point of view, but a credit card company may consider the slight increase in the total error rate to be a small price to pay for more accurate identification of individuals who do indeed default. Figure 4.75 illustrates the trade-off that results from modifying the threshold value for the posterior probability of default. The threshold is at 0.2. So look, this is, let's have a look. So what we've just done is a 0.2 threshold. And do we remember we had a 41.4 error rate? That's exactly this. When we had 0.5 as the threshold, as kind of like a default, it was 75% error rate. So much better improvement. Kind of making the model stricter, reduces the error rate. The error rate on those who default, not the overall error rate, the error rate on when it comes to predicting which customers default. This is what we're really interested in. And again, there's always this kind of trade-off. I wonder if this one, if the other curve is the customers that do not default. And that is, as you move like this, the error rate is increasing. So let's have a look. I'll look. So the blue dashed line represents the fraction of defaulting customers that are incorrectly classified. So that's really what the credit card company would be interested in. Whereas the orange dotted line indicates the fraction of errors among the non-defaulting customers. A really interesting concept. Really interesting concept. So the the price paid, if I use color green, the price paid from switching from a threshold of 50% to 20% is that the error rate for the non-defaulting customers increases from about 2%. Not that much, right? it does increase though. To around, I don't know, to around 4% or whatever. Or maybe 5%. So that's the idea. That's the idea. I wonder if there's any significance where they sort of intersect. I wonder if usually intersection points between curves are quite important. So what if we took only 5%? Only 5% reduces the. No, I don't think it's going to be of any. I can't imagine it being of any importance. You know what? You'd get the same error rate for both the defaulting and the non-defaulting, right? You'd get an error rate of around, looks like, I don't know, 12, 13%. Let's see, might be important. Might be important. And do let me know when things need repeating. We'll definitely go over them as necessary. So figure 4.7 illustrates the trade-off that results from modifying the threshold value that was originally 0.5, now 0.2, for the posterior probability of default. Various error rates are shown as a function of the threshold function using a threshold of 0.5. So the 0.5, it minimizes, by the way, the black, which is the one we didn't discuss, that's different to the orange. The black is the overall error rate. And LDA for two classifiers, default, non-default, is set up in such a way to reduce the overall error rate. But then you can change the threshold. That makes most sense for the specific scenario that you're working with. So this is expected since the base classifier uses a threshold of 0.5 and is known to have the lowest overall error rate. But when the threshold of 0.5 is used, the error rate among the individuals who default is quite high. That's the blue dashed line. It's practically highest from what we're looking at in this chart. As the threshold is reduced, the error rate among individuals who default decreases steadily, but the error rate among the individuals who do not default increases. How can we decide which threshold value is best? Such a decision must be based on domain knowledge. What we mean by domain knowledge is knowledge and experience of the industry that you're working within, such as detailed information about the costs associated with default. The ROC curve, and I think that's going to be this over here. The ROC curve is a popular graphic for simultaneously displaying the two types of errors for all possible thresholds. The name ROC is historic and comes from communications theory. It is an acronym for receiving operating characteristics. Figure 4.8 displays the ROC curve for the LDA classifier on the training data. The overall performance of a classifier summarized over all possible thresholds is given by the area under the ROC curve. Okay, so let's try and see. An ideal ROC curve will hug the top left corner. I think by hugging we mean this is as close as possible to these two black lines. So what are we plotting before we continue reading? There's the false positive rate and there's the true positive rate. Right. Right. So if we look at just before we read the book. So are we saying that for each threshold are we saying let me try and get an easy one to read. Let me just make sure. So is it literally a case of for each threshold, we're going to say this orange is the false. Is it the false positive or the false negative? I think it's the false negative, right? The function of error is among the non-defaulting. So there's a false positive. Positive means default, right? In this example, if the model incorrectly classified you as default, that is a false positive. Positive means default in this model. And this is sort of the corresponding false negative. So am I correct to say that I'm expecting and I'll type it so that we don't lose these things. We're going to have I think we're going to plot false positive against false negative. And would one of the points be like 1% against, so the 1% is just what I'm reading over here, against what looks like 55%. Let's draw another one. I wouldn't be surprised if I've got this entirely wrong. But let's try, for example, this one. What does this look like? It looks like 7%, and it looks like 25%. Let's see. No, actually, spotting something different, isn't it? It's the false positive rate against the true positive rate. So I think this is for the overall data. Look, this was correct when I was like taking different lines as we vary the threshold value for the posterior probability of default. The true positive rate is the sensitivity. the fraction of defaulters that are correctly identified using a given threshold, the fraction of defaulters that are correctly identified, the fraction of defaulters that are correctly identified, So in actual fact, the fraction of defaulters that are correctly identified, so this is nearly 40%. I think it becomes 60%. So when the threshold is, for example, 0.2, the fraction that is correctly identified, if incorrectly is 40%, correctly 60%. The false positive rate is the fraction of non-defaulters that we classify incorrectly as defaulters. The fraction of non-defaulters the false positive rate is the fraction of non-defaulters who we classify incorrectly as defaulters. So the non-defaulters are the orange. And it says that we classify incorrectly as defaulters. So this would be, you just keep it as it is, I think. So what is it? Is it like, it's like 5%? Like 5%, this line over here, 5%. And I think the book mentions these figures. Perhaps somewhere. Well, we could probably calculate them over here, right? So what does true positive rate mean? True positive rate means those that the model, from the yeses, from the defaulters, what the model really gets correct. 195 out of 333. Yeah, it's around, specifically it's 58.5%. So it's around 60%. And then we have the false positive rate is the fraction of non-defaulters that we classify incorrectly as defaulters. So it's the no's that we classify incorrectly as yeses. 235 division by 9667. Yeah, I said 5%. It's a lot. It's actually 2.5. 2.5. And this is 59. 59. So for each threshold, you're going to calculate the true positive rate for a threshold of 0.2. The true positive rate, it's the positives that you correctly classified as a positive. Positive in this situation is the defaulters. It is the defaulters that you correctly classified as defaulters. Whereas this is the false negative rate. So it is the non-defaulters that you, false negative rate, the non-defaulters that you incorrectly classified as a default. And let's see if we find this point on the ROC curve. let's see. So we need 2.5%, or is it like this? 60%, and hopefully that's 2.5%. So this point over here is one of the many points on the ROC curve. And now we need to see how to interpret this ROC curve. What would be a better ROC curve? You always want, I don't know if I just use two random colors. You want this to be as small as possible. You want your false negatives to be as small as possible. Because over here, the credit card company is incorrectly turning away customers that would have actually offered a good risk. And you want to maximize your true positive rate. The company wants to identify as many bad risks as possible. So always in an ideal situation, the closer the curve, and I'm going to use pink now. The closer the curve is like this, the more it hugs the left-hand corner. Let's take black now. Let's see. Okay, one last, okay, final attempt. Let's get this right. So the more it is like this, oh, obviously it can't go. Let's stick to the pink one. Let's stick to the pink one. Now, so for example, when you compare this point to this point, for the same false negative rate, you have a higher true positive rate. And you want a large AUC, area under the curve, area under the ROC curve. So the maximum, so what is your largest area? Your largest area is of course 1. This is a 1 by 1. That's a 1 by 1 square. You want this larger, the higher this red region is, the greater the area of this red region is. Then what actually? I mean, each point is for a different threshold, right? Remember, we're not seeing the thresholds in this in this diagram. Then what actually? I mean, isn't it just a case of choosing the threshold that gives you, let's see, an ideal ROC curve will hug the top left corner, so the larger the AUC, the better the classifier. For this data, the AUC is 95%, which is close to the maximum of 1, so would be considered very good. We expect a classifier that performs no better than chance to have an AUC of 0.5 when evaluated on an independent test set, not used in model training. A classifier that performs no better than random chance, okay? ROC curves are useful for comparing different classifiers. What do we mean by different classifiers? Do we mean just the predictor variables that we've used? Aren't the classifiers just default, non-default? maybe I've missed something. Since they take into account all possible thresholds, it turns out that the ROC curve for the logistic regression model of section 4.3.4 of the regression model, it turns out that the ROC curve for the logistic regression model fit to these data is virtually indistinguishable from the LDA model, so we do not display it here. As we have seen above, varying the classifier threshold changes its true positive and false positive rates. It's true positive and false positive rates. These are also called the sensitivity and 1 minus the specificity of our classifier. Since there is an almost bewildering array of terms used in this context, we will now give a summary. Table 4.6 shows the possible results when applying a classifier or diagnostic test to a population. To make the connection with the epidemiology literature, we think of positive as the disease that we are trying to detect and negative as the non-disease state. To make the connection to the classical hypothesis testing literature, we think of negative as the null hypothesis. Okay, I'm lost. Can we live without this table? I think we can. I think we can live without it. So I'm actually gonna skip this very last section, and we're going to move on to something similar, but it's now the quadratic discriminant analysis. And if you ever want to take a break at some point, but I'm more than happy. As we have discussed, LDA assumes that the observations within each class are drawn from a multivariate Gaussian distribution with a class-specific mean vector and a covariance matrix that is common to all. Yes, I'll just read this last sentence and we'll continue in 5 minutes. That is common to all K classes. Quadratic discriminant analysis, QDA, provides an alternative approach, but we'll pause the recording right now. Continuing, like LDA, the QDA classifier results from, or classifies, I think is that maybe a minor typo. Like LDA, the QDA classifies results from assuming that the observations from each class are drawn from a Gaussian distribution and plugging estimates for the parameters into Bayes' theorem in order to perform prediction. Now, where's the difference? However, unlike LDA, QDA assumes that each class has its own covariance matrix. So this is a bit more powerful now. That is, it assumes that an observation from the kth class is of the form, and notice the indices. We now have a K not only for the mean, but for the covariance matrix. Don't get too caught up in what we on the details of covariance matrix. It's just going back to those ellipses that we had earlier. Just think of the sigma as giving you a description of the width, but also sort of if the ellipse, it kind of rotates the ellipse as well, depending on the values, whether you get positive correlation or negative correlation, these kind of things. It's not too important for this chapter. At least it hasn't been so far. Where sigma k is a covariance matrix for the kth class. under this observation, the base classifier assigns an observation x equals k to the class for which this expression evaluates the largest real number. So the QDA classifier involves plugging estimates for the covariance matrix K, mu K, and pi K into 4.23, and then assigning an observation x equals x to the class for which this quantity is largest. Unlike in 4.19, the quantity x appears as a quadratic function in 4.23. And where does it appear as a quadratic function? I think it's, you know where it appears as quadratic? Because you're multiplying the transpose of x by x. So for example, over here, it is a linear term in x. So I'll use pink for linear, and I'll use red for quadratic. In many ways, it's like O levels ax squared plus bx plus c. Quadratic, linear in x, and constant in x. Why does it matter whether we assume that the k classes share a common covariance matrix? In other words, why would one prefer LDA to QDA or vice versa? The answer lies in the bias variance trade-off, which is now a good time maybe to quickly go to chapter 2 and look at bias variance trade-off. This is when we had section 2.2.2, when we were dealing with I'd spent a lot of time on this one, I seem to remember. Bias against variance. Let's see. It's two competing properties. The bias and the variance. Okay, so now the error term might make an appearance. I had mentioned this a couple of sessions ago, that chapter 4 nowhere mentions an error term epsilon. Let's just go back and see. Let's see what we're going to say now. What I like about this book is you can quickly make each page. It uses large fonts and can actually get a lot done. We're nearly on page 150. When there are P predictors, then estimating a covariance matrix requires estimating. Do you know why this is true? That's nothing but it's basically the area of a triangle. So if you have your P by P, if this is your sigma matrix, if that's just think of them as P values by P values. So if this is your sigma, it's symmetric. So all you need to know is the diagonal values and the ones and the values above. Or the lower triangle will have the same values. It will be symmetric about this diagonal. And how many of them are there? There are P times P plus 1 division by 2. It's not P squared times P squared division by 2, because you also need to allow for the numbers on the leading diagonal. So you need, for your sigma, you need these P times P plus 1 divided by 2 parameters. QDA estimates a separate covariance matrix for each class. So of course, you're going to need K times, in LDA, you just estimate one covariance matrix. But in QDA, you need a covariance matrix for each class. So if you have 50 predictors, that is a multiple of, if you're just using LDA, you would need the 1, 2, 2, 5. So, right, it's 50 times 51 division by 2. But you would now need 1, 2, 2, 5 parameters for each of the K classes. So if you have 3 classes, seizure, stroke, and overdose, you'll now need nearly 4,000 parameters for all your covariances. But instead of assuming that the K classes share a common covariance matrix, the LDA model becomes linear in X, which means that there are KP linear coefficients to estimate. KP. KP. Is it because of the mu k's? Not entirely sure. Anyway, let's look at this diagram very quickly. So left, the base purple. So base is purple. You never have the base purple. They have it because they kind of did this in the opposite direction that you would normally do it. They already had the true distributions, which is a common theme so far in this book. That we used to describe this at the beginning of this course as playing God. So you already know the true distributions. So you can actually calculate the true Bayes decision line. Then there's the LDA, which is the black dotted line, and the QDA, which is this green boundary. So that's on the left. Since the Bayes decision boundary is linear, it is more accurately approximated by LDA. But on the right, so on the left, the two covariance matrices were in fact equal to each other. So you can just use linear. But you know, as would often be in the case in real life, if the covariance matrices are not equal to each other, then QDA is better than LDA. QDA gives you this green, which is a lot closer to the true purple decision line. Okay, so LDA is a much less flexible classifier than QDA, and so has substantially lower variance. This can potentially lead to improved prediction performance, but there is a trade-off, isn't there always? If LDA's assumption that the K classes share a common covariance matrix is badly off, then LDA can suffer from high bias. Roughly speaking, LDA tends to be a better bet than QDA if there are relatively few training observations, and so reducing variance is crucial. In contrast, QDA is recommended if the training set is very large, so that the variance of the classifier is not a major concern, or if the assumption of a common covariance matrix for the k-classes is clearly untenable. The figure that we just saw above illustrates the performance of LDA and QDA in two scenarios. In the left-hand panel, the two Gaussian classes have a common correlation of 0.7 between x1 and x2. As a result, the Bayes decision boundary is linear and is accurately approximated by the LDA decision boundary. The QDA decision boundary is inferior because it suffers from higher variance without a corresponding decrease in bias. In contrast, the right-hand panel displays a situation in which the orange class has a correlation of 0.7, but the blue class a correlation of negative 0.7. So what are we saying over here? The orange had a 0.7 correlation, so did the blue, a 0.7 correlation. Now we have a negative 0.7 and a positive. So even those ellipses are very, very different now. This ellipse is something, try and use the same colors. This ellipse is something like this. But this ellipse, and again, I really like the colors to match. This ellipse is something like this. So you definitely want the QDA to reflect the significant differences between covariances. Now, this is something I don't really want to do. Let's see how long it is. It's not too long, actually. It's like 3 pages. But I think we can ignore it for the time being. Which actually means that we can now perhaps start discussing. We did this in our previous session. We can now start discussing. Just going to look at my phone for a second. We had done the stock market data, where we actually saw that the predictor variables that we're using weren't that useful. No, we hadn't done this. Okay, so let's move on to. Oh, is it still market data? I was hoping. I mean, in the exercises, they'll probably tell us to use a different data set. So the weekly data set. This data is similar in nature to the market data, except it contains 1089 weekly returns for 21 years. Now we move on to chapter 5 after. But we need some more experience in R. Linear discriminant analysis. I guess the question is, do we kind of go over what we had done working on the stock market data? We had used logistic regression using the GLM function. Are we taking an out of, a holdout data set? So you only use as your training data set, you only use you're partitioning your data into into two segments. The data that's less than 2005 and the data that is not less than. When you say exclamation mark, that means not. So let's have a look. If you type so true is a reserved value. If you type this, you now get false. It's negation. Those of you who are doing logic right now, logic negation very often is represented by that symbol. So if you have a statement, Q, its negation, maybe not such a long line, but its negation would be not Q. So actually, it might be worth putting, if I share my screen and put these side by side. One thing is that when we do this, we lose the full screen view, which tends to limit what we're looking at. You can improve, you can remove the menu bar. One thing is, I don't know why it's asking me for a signature. So in an ideal world, I would like to remove this banner, but it's easier than I expected. Okay, so let's see. Yeah, I think this is in fact where we had got to last time, where we had this confusion matrix. And which ones were we getting? Which ones did we get right? We got 145 of these downs correct, and we got 507 of these ups correct. So for whatever reason, it seems to do a better job of predicting the ups correctly than the downs correctly. If you add these two values, that's 652, and that should give us the error rate, right? So we correctly predicted the way the market was going to move the next day based on the information of the previous. Remember when we said I was expecting, or when I said I was expecting more days? Is this 5 years of data? So it's 5 years of data, and I naively multiplied 365 by 5, and I said, okay, I was actually expecting 1825. Of course, I didn't allow for weekends. So in actual fact, why do we have 1250 days? Because there are how many weekdays in a year? Where roughly it's 517 times 365. So they're roughly 260. And if you multiply by 5, you actually get 1303, which is now a lot closer to the 1250 days. There might be other days where the stock exchange doesn't open. Not exactly my field of expertise, if you will, but that's clearly what's going on. So this model, looking at all the training data, gets the predictions correct 652 times out of a total of 1250, which is in fact that 52.2%. And then we say, at first glance, it appears that the logistic regression, which is what we were using to this point, model, is working a little better than random guessing. However, this result is misleading because we trained and tested the model on the same set of 1250 observations. In other words, 47.8% is the training error rate. As we have seen previously, the training error rate is often overly optimistic. It tends to underestimate the test error rate. In order to better assess the accuracy of the logistic regression model in this setting, we can fit the model using part of the data and then examine how well it predicts the held out data. This will yield a more realistic error rate in the sense that in practice, we will be interested in our model's performance, not on the data that we use to fit the model, but rather on days in the future for which the market's movements are unknown. So the way we're going to do it is we're going to pretend, you can think of it as us saying that we only have the data available until the end of 2004. So imagine we're going back, what is at this point nearly 20 years back in time to 2004. And that's all we have. That's all we have. But to really make it believable, we're going to remove the 2005 data. Now let's see, what can I get away with removing without complicating things? I think I can delete. I'll just delete everything with the exception of the first two lines. But actually, we don't want to work with default. We're looking at the market data. Okay, and sorry, what is going on over here? And just type that again. Okay, look at the structure of that data. And that's this over here. Now what we're going to do is we're going to say, maybe we should. So if the book simply types your, R doesn't understand what your is, unless you tell it to attach the data, which I've mentioned before, tends to be frowned upon in certain contexts. So where are we attaching? Here we go. So we're going to attach the data. Attach. And that hasn't worked. Do I need to? Maybe because I need to run everything again. The following objects are masked from S market. I don't know what that means. So if I now type here, yeah, now just gives me the values of all the yours, without having to tell it each time. Hey, listen, I need you to look at the S market dataset. Okay, so train is We're simply saying year less than 2005. And if we do that, what is train? Okay, so it's just trues and falses. So for the time being, train is just a vector. But in each of its position, it's telling you in the S market dataset, is there less than 2005, or which would get a true, or is there something else which would get a false? And now we're going to create a new data set, S market underscore or dot 2005. And what we're going to save into this data set is just S market, but for which I guess this works, for which train is false. For which train is false. So this is one way of like excluding data from your data set. Think of it as if you've ever filtered in Excel or similar. I'm looking for my exclamation mark in the meantime. Like this. So if I now do structure and I give it this data set, it's no longer going to tell me 1250 observations. It's only 25 observations. And notice that the year is just the 2005 years. So what have we done? We've taken S market, row by column. We've taken all the columns, comma nothing means all the columns. But we're saying when train is false. So when train is true when year is less than 2005, so we're taking everything else. And the book invites us to calculate the dimension, and that didn't work. Okay, now that worked. 252 observations, 9 fields. Okay. And what does direction do? Let's see. Direction. It doesn't explain direction. Direction 2005. And we're going to save. Yeah, I think direction is something that we had used earlier, which is why it was probably a bad idea to just delete everything. Direction. Let's find it. Oh, direction is one of the variables. Direction is just up and down. Okay, that direction is in fact what we're trying to predict, correct? Is the market today, given the information that we have over the past 5 days, and the volume, I think, as well. Okay, so direction 2005 is direction when train is false. When train, this is a vector, so we don't do a comma. We don't have rows and columns. We just have a list of, call them values. So what is this doing? Remember, we've attached the data. So this direction is all the directions in the full data set. So 1250 ups and downs. And we've now created a vector that only contains the ups and downs for year 2005. Okay. So the object train is a vector of 1250 elements corresponding to the observations in our dataset. The elements of the vector that correspond to observations that occurred before 2005 are set to true, whereas those that correspond to observations in 05 are set to false. The object train is a Boolean vector since its elements are true and false. Boolean vectors can be used to obtain a subset of the rows or columns of a dataset. For instance, the command smarketTrain would pick out a submatrix of the stock market dataset corresponding only to the dates before 05, since those are the ones for which the elements of train are true. The exclamation mark symbol can be used to reverse all of the elements of a Boolean vector. That is, exclamation mark train is a vector similar to train, except that the elements are true in train get swapped to false, and you get the picture. False become true. Therefore, smarket brackets exclamation mark train comma yields a submatrix of the stock market data containing only the observations for which train is false. That is, the observations with dates in 2005. The output above indicates that there are 252 observations satisfying that condition. We now fit a logistic regression model using only the subset of the observations that correspond to dates before 2005. This is exactly what you would do. Were we, right now we're at the end of 2022, but were we at the end of 2004, we wouldn't, unless we're time travelers, we wouldn't have information of 2005. And we're only going to look at the data before 2005. And you can see that over here. It's interesting, you can tell it data equals smarket, but then you give it a subset. I didn't know there was that feature. I was thinking, just like we created smarket 2005, we would create smarket. For example, I know what you'd name it. You'd name it, for example, until 2004. It's not quite the case. We then obtain predicted probabilities of the stock market going up for each of the days in our test set. That is for the days in 2005. So look, it's a two-step process. You first create the model using only, when we say create the model, this is logistic regression, correct? You're selecting the parameters based only on smarket, but smarket where the observations satisfy the train condition, which is this over here. So that's step number one. Now you're going to check the effectiveness of your model. Imagine that now you're going to use the model on every day of 2005. So 1st of January comes and you make a prediction based on the last 5 days. Then 2nd January, you make another prediction. 3rd of January, make another prediction. 4th of January, you need to do this on a daily basis, though. This is just how the data is. If I want to make a prediction for the 20th of January 2005, I need to wait practically till that day, because to make the prediction using this model, I need the information of the 5 previous days. So you make your prediction now. You make your predictions based on the data in the 2005 dataset. And the parameters, I'll use color blue, the parameters that you estimated in what we just called, we called our model GLN fit. Notice that we have trained or tested our model on two completely separate datasets. Training was performed using only the dates before 2005, and testing was performed using only the dates in 2005. Finally, we compute the predictions for 2005 and compare them to the actual movements of the market over that time period. And now we've got 77 from the downs correct, and we got 44 of the ups correct. So this is a lot worse than that 52% that we had earlier. Or is it? Out of 252. Yeah, it's not much worse, but it says than half. It's going to be 48. It's going to be 48%. As you would expect, it's worse now when we're using an out-of-sample data set. The test error is worse. The results are rather disappointing. The test error rate is 52%. We only got 48% correct, which is worse than random guessing. Of course, this result is not all that surprising, given that one would not generally expect to be able to use previous day's returns to predict future market performance. Well, that might come as news to some people. We recall that the logistic regression model had very underwhelming p-values associated. Do you remember these p-values? These all pretty bad. What you normally want is, 0.01 gives you an idea that there might actually be a relationship between what you're trying to predict and what you're using to predict it. And have I? Yeah, we're way off. We are on this page. Perhaps by removing the variables that appear not to be helpful in predicting the direction up-down, we can obtain a more effective model. After all, using predictors that have no relationship with the response tends to cause a deterioration in the test error rate, since such predictors cause an increase in variance without a corresponding decrease in bias. And so removing such predictors may in turn yield an improvement. Below, we have refit the logistic regression using just lag 1 and lag 2. Lag 1 and lag 2. Which seem to have the highest predictive power in the original regression model. And now this gives us, again, we've basically just repeated what we've just said, looking just at the training subset and then predicting based on the out of sample predictor characteristics. And now we predict 35% of the downs correctly and 106 of the ups correctly. Next session, we can move on to linear discriminant analysis. And the code will use the LDA function. Unfortunately, it doesn't do an ROC curve, but to my knowledge, there is a package that it might not be mentioned in this book. I think it's trying to avoid over-reliance on external packages besides the one that comes bundled with the material that we're using. But in that case, that would mean that we're now going to start resampling methods. And if we look at any of the diagrams, hard to say what to expect over here. Is it a very long chapter? So it takes us to page 201. So it is around 50 pages in length. And then we have chapter 6, but that will be, you know, for the coming months. Can stop over here.